All right, welcome to the after work video. Um, Working on this book, Machine Learning for Network and Cloud Engineers. I'm very nearly complete. We just got 85 more pages to read. We're almost 80% of the way there. These come with Jupyter notebooks for the use case. So I'm going to open the notebook for this one. Now, in the last use case, I'm doing this differently than how the author intends. The author wants you to use a Google Colab notebook up on Google Drive. I'm using my own hardware just because uh, I just want to do it that way. I have a nice GPU that can be used for gaming on high settings. So like I just kind of want to do it that way. I want the challenge too. I want to see like the error messages. I so, but unfortunately, the challenge was just too much for use case 8. My hardware just couldn't support the demands that were needed. AI really scales up fast, so no matter how nice of a gaming rig you have, at some point you need a dedicated AI rig, and then at that point, that is not even going to be enough. AI is something that's you know uh, a really great channel that I will recommend. A shout out is Darkesh. If you're following me, stop following me now. He does a lot of interviews. He doesn't do technical deep dives and like read books and stuff like I do. But these are basically the actual people sitting in front of the computers working on artificial intelligence. So this was a great one here. It's a 4.5 hour interview with one of the brightest minds in technology. And one thing he said in the interview was $1 trillion data center. So that's what you need to make the next generation of AIs. And in fact, the current generation of AIs with ChatGPT, let's ask it that. So, how much money was needed to create ChatGPT? This is one of the whole things. It's called OpenAI, the company that created ChatGPT, because they wanted it to be open. They wanted it to be centered around open source, and they wanted it to have those kinds of philosophies and to be different from a regular company. But one of the big controversies is that's not as effective of a way as to bring in capital, to bring in venture capitalist money, or just money in general. That's just not a good way. That's just not as effective of a way to do it, is what I understand there. So they kind of set some of those principles aside, or were more flexible with them, to just get the money they needed to create ChatGPT. And we can see here.
Creating ChatGPT, an advanced AI language model, involves substantial investments in several areas, including research and development, computational resources, data acquisition, and operational expenses. While the exact cost to create ChatGPT isn't publicly disclosed by
Okay. Well, the exact cost isn't. Oh, right. So, yeah, according to some estimates, just for training is 5 million to 12 million. And it does not include research and development. So, like all the salaries, the data acquisition, ongoing operational expenses. So, yeah, even if you have a really good gaming computer, um, that's not going to be enough very quick. If you have your own dedicated, so if I made my own dedicated home AI setup, what could I expect to spend to like have something that's pretty decent? Yeah, so you can make a dedicated setup, but it's gonna cost you um, $3,000 to $25,000. So this isn't like a gaming PC at all. A gaming PC, $1,000, you should be able to play any game out there. Some gamers get crazy and spend more than that, but I feel like you don't have to. I mean, there's a point where like just buy like an Xbox and play the game, like, but so when it comes to doing AI intensive things on your computer, if you have a gaming PC, you're going to run out of that pretty fast. You really need a dedicated AI computer at some point. So that's going to cost you, just to set it up, $3,000 minimum. And if you want something that actually works, it's going to be $25,000 plus. And if you want to do something like train and create ChatGPT, that's going to cost you $5 million. So that's kind of the whole insight in how we're having these advances in ChatGPT. Scaling. If you scale things up, you throw in power into it, which costs money, then you can continue to make progress in it. So these are inaccessible to just you or I, to a point of the complexity. But the good news was all the other use cases were able to run fine on my hardware that I have. And then even better news, I guarantee you if I would use Google Drive and a Google Cloud Notebook, I could have gotten that to run. So I'm not going to go back and do that. I just feel like it's not worth it. Especially since you get the benefit of using Google Drive is you get free GPU and TPU usage, but it's a cloud service. So you get a cutoff, then you can pay for more. And as we've shown here, if you really want to do something significant, you're going to have to pay quite a bit. So, all right, so moving on. I will now introduce a new concept, incremental training. So far in the previous use cases, we have worked under the assumption that we have all the data we need to train a model, and we simply loaded it in memory and trained the model. There are other cases where having all the data in memory is not possible because A, you do not have the data. The data is coming constantly, and you cannot assume that a capture of the older data is enough. B, the amount of data is too large and does not fit in memory. C, data is in frequent evolution, so you need a sort of online training that gets trained as new data comes. Sorry, I have to. Okay. Sorry about that. I want to use my desk treadmill. By whatever reason, you need some way to train your model in batches of data in a way that could be potentially continuous, as new batches of data may be compiled from an incoming stream. Yeah, sorry about that. The tread in the treadmill is miscalibrated, so I have to fix this. Okay, there. And I damaged it a little. Whoops. Oh. Okay. All right, there we go. So, by whatever reason, you may need some way to train your model in batches of data in a way that could be potentially continuous, as new batches of data may be compiled from an incoming stream. In our case, I was planning to run the training of the autoencoder in incremental mode, and also the training of the GAN will work in incremental mode. You may note, though, that the autoencoder notebook file name refers to in-memory because I ended up using a non-incremental approach for the autoencoder training, but the code was developed for incremental training. I will explain you the logic and differences so you can, when you need to use one or the other based on your requirements. So that sentence should say, I will explain to you the logic and differences so you can decide in the case that you would need to use one or the other based on, yeah. Well, I guess it makes sense. I will explain you the logic so that you can explain it too. But there should be a two there. When you need to use one or the other based on your requirements. Let's start by setting a few variables for our training process. All right, so we're working with the notebook, so I'm going to get that up and running. All right, so, yep, I've got running there. So, here we go, use case 9. And yeah, this is the in-memory one it was referred to. All right, so yeah, and you know what? I am gonna do this on my local. If I run out of memory, if the kernel crashes, I will switch over to doing this in Drive, because if it's going to be a memory intensive thing, yeah, as we saw, the requirements of AI are massive. So if you spend $25,000, you might end up not having enough power for an AI application. All right, so we're going to open up the so we're gonna run it locally for now, and then if it doesn't work, then I will run it in Google Drive. Okay, and this is use case 9. There is one more use case. I'm not sure if there's a notebook associated with that, though, because I don't see it there. But okay, so we'll do kernel, restart and clear all, and then we need to change sans as well. Right, and I don't see those warnings. We should get those warnings saying, yeah, there we go. The other, yeah, so I misconfigured my my GPU. I don't have, I didn't use, right. So this TensorFlow binary is optimized to use available CPU instructions in performance critical operations. To enable the following instructions, AVX2 FMA, in other operations. Yeah, so that could be something to consider if I were really serious about trying to use my home gear for something. But the other one, TensorRT, I don't think I'll need that. All right, so moving on. And this is a big one. We got to get a data frame here, so it takes a few minutes to generate the data frame. Okay, so this is a. So we'll leave that to cook and then keep reading. Most of the variables, you probably have a good intuition about what they are about. Previously, though, we had not specified here the training or validation steps per epoch. Why do we do that now? Because when we train the model incrementally, we will be asking the system to generate training data. There is a concept of data generator. Effectively, this means some function needs to make some batch of data available for the training process. Once such a batch has been processed, the generator is called again to provide more data, and so on, until the number of epochs that has been configured finishes. Therefore, instead of providing a big matrix as input, we offer small chunks of data which feed the training process. We need a dictionary to match characters to numbers. Since we are using the same set of logs as in previous use cases, we are going to use the same dictionary we had already saved. Next, a few functions are defined that will be part of the processing of every log batch as it is loaded from the file. The following function is intended to remove logs too long that max exceed the defined threshold. In our case, there is none, but let's pretend there could be, hence the reason for the function. The next function will receive a list of logs and produce a tokenized, in this case at the character level. And I don't know if that's the right word. It will produce a tokenized. I think it will produce a token maybe, but I'm not sure. Okay. So next, with the following function, given a list of already tokenized logs, it will return an array with those logs in a one-hot encoded format, doing the mapping of each character to the dictionary. In the following function, given a file handle, it will load a batch underscore size worth of data. The next function is the key to enable incremental training. As you can see, it is an infinite loop where a batch of data is loaded. It is processed and converted in a one-hot encoded matrix, and then it is returned using the yield command. The yield command will return the data and continue execution as opposed to the normal return command in a function that will end the execution. This function will iterate through the file, fetching batches of logs, and will return to the start of the file once we reach the final in such an endless loop. Okay, so the yield function, yeah, the yield statement. What would you call it? You call it the yield command. Yeah, command. It's kind of a. Let me ask ChatGPT about that. Okay, so I have like a network engineering background, so like I'm really comfortable with using the word command because like, you know, you enter commands into a networking device, and I think this kind of verbiage also makes a lot of sense for just working in Linux. You know, you enter commands at the command line. It's literally called the command line interface. So like I'm really comfortable with using the command word in that context, but where I'm wondering if it's appropriate to use the word command is when you're coding. So for example, you're writing a function in Python and you end the function with with return. Is that the return command? Let's say that you end it with yield instead. Would that be the yield command? Is that what you could call that in that context? A command? Does that fit there?
In the context of programming, especially in languages like Python, the term command is typically used to describe statements like return or yield.
You'd say it's
instead,
a statement.
these are usually referred to as statements or keywords.
Yeah.
Here's a bit more detail. Return statement. When you write a function and use return, it's commonly referred to as the return statement.
Exactly.
For example, here, return 42 is the return statement.
Yeah, so the author kind of gave himself away. He's a network engineer like I am. You really wouldn't call something like that a command. You would call it a statement. And it might even make things confusing because let's say you want to actually run a command on the command line interface. Say you're using like NetMiko, you reach out to a networking device, or say you're executing a command in the machine that you're running the script on. You know, you can get things confused very quickly if you don't use the right language there. So yeah, the author kind of outed himself as a network engineer there, which is great for this book. Yeah, that's typically in network engineering what you would call, you know, programming a device or like configuring a device. You would call everything a command pretty much. But in code, it's different. They aren't commands, they're statements. It's much better to call them statements than commands. All right, so to effectively implement incremental training, we would define an instance of the batch underscore generator function given our specific set of parameters that will be used as a parameter in our training function as depicted in the following code snippet. This would instruct the model to use the referred data batch generator to get new batches of data. In this way, the only memory resources required are those necessary for a batch worth of data, not for the entire data set. Note, though, if you look for this code in the notebook, you will not find it because I ended up simply loading all data into memory. I wanted, however, to explain how this would be done, and we will effectively use this strategy in the second part of the use case, the GAN training itself. The following is the function I ended up using to load the data. Instead of using the incremental data generator, the following code uses a similar structure but loads all the data requested at once and returns a complete one-hot encoded data frame. When we run the above function, we obtain the entire training data that we will use in our training function, effectively doing an in-memory training rather than incremental. But at least you should have a sense of how different it would be should we take an incremental approach. By now we have the data ready for consumption by a machine learning model. You may have noticed that we only have x underscore train and there is no y underscore train because we are going to train an autoencoder and the output of the model is expected to be the same as the input. We will use x underscore train as the labels. Let's have a look at the autoencoder model. The following diagram shows a graphical representation of it. All right, and what I've been doing is, now I'm opening Signal for some reason. So I'm typing in snipping tool, and I've been feeding these to ChatGPT to get a explanation of it.
This image illustrates the architecture of a sequence-to-sequence autoencoder model using long short-term memory (LSTM) layers for processing time series data. Encoder input matrix. The input of the model is an NX210 by 68 matrix, where n is the number of observations, 210 is the sequence length, and 68 is the number of features. LSTM layers. The encoder comprises stacked LSTM layers. The input vector shape is processed through the LSTM layers, resulting in a 68 by 210 output. Latent vector. The output of the encoder is a latent vector with a shape of 512 by 1. Decoder repeat vector layer. The latent vector is repeated to match the required sequence length, resulting in a shape of 210. Bidirectional LSTM layer. The repeated latent vector passes through a bidirectional LSTM layer, producing an output. Time-distributed dense layers. The output of the LSTM layers is processed through time-distributed dense layers to reconstruct the original input dimensions, resulting in an output matrix of shape 68 by 210. Overall flow of the input matrix is fed into the encoder, which compresses it into a latent representation. The decoder then reconstructs the sequence from the latent representation to produce an output matrix with the same shape as the input. This model is designed to learn efficient representations of sequences and can be applied in various time series forecasting, anomaly detection, or sequence generation tasks. If you need any specific analysis or further information on this model, feel free to ask.
All right, so I kind of wasn't listening. Okay, so moving on to the next cells in the notebook. We had this cell running good now, so we're up to date with what's in here, so let's keep on reading. The main thing to note is that you may find it strange that after the second layer of LSTM in the encoder. The size of the latent vector is 512 by 1, but the number of nodes in the LSTM layer that produces it is 256. Usually each node in the LSTM will produce one output, so you might have expected a 256 by 1 vector. However, we are using bidirectional LSTM, which effectively means the unroll process of the LSTM across the sequence, the 210 characters, happens in both directions, from left to right forward, and from right to left backwards. Therefore, our latent space has the output of the rightmost LSTM module for the forward direction, and from the leftmost LSTM module for the backward direction. The combination of the two sites in the 512 by 1 vector in the latent space. This model has close to 4 million trainable parameters. All right, so let's do model that summary and close this. This opened on its own. Okay, so this is interesting. How many trainable parameters? Okay, so we've got close to 4 million. What does the book say that they would have? Oh yeah, okay. So it's lining up with that. Okay. We are ready to compile the model and run the training. As our model is effectively doing a multi-class classification, we are predicting each character in the log out of 68 different possible options, which is the length of our dictionary. We need the categorical cross-entropy loss function, as well as categorical accuracy as metric. All right. The training process for this model is slow. Assuming Google Colab with GPU, it takes about 5 minutes per epoch. It converges slowly but steadily, fortunately. However, after the first epochs, the improvement slows down considerably. The autoencoder plays a key role in our use case, so I need it to be as good as possible. Therefore, I have run the training a couple of times to try to get a better accuracy. In aggregate, it has run for about 40 epochs. The weights for the end result are saved as weights underscore autoencoder underscore best .hdf5. Therefore, you do not need to do the training. You can simply load those weights and start your training from there, or skip the training and simply use those weights. All right, so 5 minutes per epoch, hundreds of epoch, 144 epochs there. So I'll kick it off, but I think we are gonna have to load in those preloaded weights. So here's where it would load in the preloaded weights, and I think this is the command. Oh, interesting. I think this history command down here is where you would. Interesting. Oh, yeah. So this is where weights autoencoder best. So we have to change that here. In use case 9. All right. All right, so we got an unexpected keyword argument here. So there's something, maybe because of the version of the package that I'm using, it's unexpected there. So let's do a help on my model.fit, and then keep the output clean by commenting out the other line. And then we're going to do a run. And now we can see what the acceptable keyword arguments are. So here's a description of the keyword arguments. So verbose, yep, callbacks, and then another one is validation split, validation data, shuffle, class weight, sample weight. So I'm not seeing anything about multiprocessing. So yeah, it looks like it doesn't have a keyword argument for multiprocessing. So I guess what we could do is just remove that and see what happens. Hopefully it doesn't have to multiprocess. But yeah, I must be using a different version. Maybe in the newer version it multiprocesses, and there's not the option to not have it work that way. So yeah, that should be the answer, is to just remove this last keyword argument because it doesn't exist. And hopefully that fixes the issue. So I thought the book, yeah, so the book said that there was a command that will take 5 minutes per epoch. I think that's this command. So we're trying to load the weights with this command. So I think we already have it. So it's the log generator autoencoder model. I mean, we already have the files and everything. Yeah, we shouldn't have to rely on that. Join is not defined. Yeah, so this is yeah, so we had a problem cell. The kernel failed when we tried to run this cell. Okay, so let's restart and clear all, and then try to get back there. And this is what happened in the last notebook. As it said, it takes 5 minutes per epoch in Google Colab, which has more horsepower than I do. So for me, it's just going to crash the kernel and not even get anywhere. It just requires more resources than I have. And it requires, even if I had the resources, it would have to be professionally set up and configured. All right, so here's where we get back there. If we it should run now, hopefully. This cell will error out because we're not yeah, because wait, where does this come from? Oh, I don't know where this comes from. Oh, it comes from my model. So it's my model.save, and then you give it a name. So we're doing things to the model. So what we can do is we can initiate the model. We can add our parameters to it. We can get a summary of the model that we initiated. We can even compile the model. We can load weights into the model. We can create checkpoints within the models. But when we do a .fit on the model, then the notebook crashes. So you can't do that. So we can save the model as well, but it won't have the fit. But let's try that. Let's try saving the model. Hopefully the kernel won't crash here. But generating that data frame takes a while. So in the meantime, let's keep reading. At the end of the second round of training, we are obtaining categorical accuracy for validation of data of around 84%. This is good enough for our exercise. I am sure there are ways to make this better by finding a better autoencoder architecture, fine-tuning layers, etc. But I will leave that to you in the further work section. Total performance when we run all our training data is about 83%. we have defined the same functions as in the previous use case that would allow us to transform back to a human readable format from the matrix of probabilities that the model produces as output. When we do that and compare one original log with its reconstructed version by the autoencoder, this is how it looks like. All right, so this is the log message. Remember, where this use case is for generating fake logs. The first one is the reconstructed version of the log. The second one is the original. You can see how the model is trying to produce a similar sequence. It falls in some areas of the log, but you can see there is a good level of similarity. Now it is time to break our autoencoder into its two pieces, the autoencoder and the decoder. We will need them separately in the remaining part of this use case. We need to extract each layer's weights and save them for the encoder and decoder parts so we can load them later on the notebook where we will work on the GAN. Let's extract the weights for each of the layers and keep them separately. Now we can create two new models, the encoder and decoder, by only using the layers that are involved in each. We define the layers, copy the weights from the complete model by selecting only the layers that correspond, and then we can save the weights for use in the GAN. All right. We can visualize, as in the previous use case, the accuracy of the model across different positions along the log message and observe where the model is stronger or weaker. Looks good to me. And what happened here? Did the kernel crash? The kernel did not crash. It's still working on generating that data frame, which can take quite a while. In general, we have obtained better results than in the log prediction use case, but there are still areas where the autoencoder struggles to reconstruct properly the original log. Now that we have broken our autoencoder in the encoder and decoder parts, we can do some exploration on how the data looks like in the latent space. Logs are transformed first by the encoder into a 512 by 1 vector. How do similar logs look in that n-dimensional space? I have defined a small routine to color differently logs from a certain type. In particular, in this example, logs that contain the string if_mgr. All right, there we go. So coloration of the log should be different. Let's check back in here. Still going. We will use the sequence generated of R and B to color data points in a plot of the latent space data. But latent space data is a 512 dimensional vector that is not easily representable. In the theory section, we say in the dimensionality reduction section that there is a nonlinear dimensionality reduction technique called TSNE. Using TSNE, we can project the latent space into a more consumable 2D or 3D space. We will do a mapping into 2 dimensions so we can visualize them using a scatter plot. Oh, yeah. Okay. That'd be cool to get that working. So we got the data frame to generate now. It takes a while. We're still having so we're having an error here. It has to be named. So we can't synchronously open the file. Okay, so we got kind of an interesting error here. Yeah, so there's yeah, I think this has to be named Keras. There you go. It's not a zip file, so this one does have to be. Uh, okay, so this has to be. Man. Yeah, I don't think I'm handling these files correctly. I think that might have been part of why it failed in the last video. And we can look at the other use case because I'm pretty sure I had to. Yeah. So you know what? This is so I named it .weights.h5, uh, and it looks like that's probably fixed the issue. Huh. Interesting. Oh, still not a zip file. Oh, right, because I have to rename it. So back to use case 9. Down here, it's going to be HDF5. All right. Okay, so it hasn't crashed yet. All right, and now we can't. Okay, so uh yeah, so let's do that cares. All right, looks good to me. So now we get an accuracy. So this is another action um, against the model. It's too much for it. It's failing there. Let's take a look at that extra file. It was something called model. Did it create that? Yeah, it created that here. So let's open it anyway. Yeah, we really can't see anything there. There's the metadata is in JSON, but the rest is compiled, so it doesn't show up. It just shows up as basically random Unicode characters. Okay, so then yeah, so let's try renaming this to weights.hd. Nope. So now let's. Oh, we'll open it anyway. Okay, no, it's not. So let's try HDF5. Okay, so yep, it's not an FD. It's not that sort of file. So unfortunately, we might not be able to move forward because the kernel crashed. So you can see we're running at 1. None of the things are defined anymore. So yeah, dealing with the my model object, it will likely result in a kernel crash, likely because I just don't have the horsepower for it. It's meant to be done on Google Colab, or if I do, it's not configured right, as we saw with those prior warnings. All right, so yeah, you know what? I kind of want to just skip it, and just keep reading. We can see how all logs of that type appear to be quite close in the latent space. If you play with different log types, you will see that they correspond to other clusters. As you can notice, the encoder has truly captured the patterns and similarities. Similar logs are very close in the latent space, so somehow those 512 by 1 numbers of the latent vectors are semantically representative of the log. We have finished with the work with the autoencoder creation. However, we need one more step that we can do as preparation for the work with the GAN. As we have determined, the GAN components will work in the latent space. We have the option to run the encoder in real time during the process of training the GAN, or alternatively, we can offline transform all our logs into their latent space representations by running now the encoder part. This will allow us to simplify and accelerate the GAN training process because logs will be already in the right format. Therefore, we will proceed now to generate a new training file that contains the logs, but it is latent space numerical representation. Alright, so yeah, I guess I'm going to give up on the notebook. I could do it in Drive, that might be a good... And then I can demo actually doing it in Drive, because anyone watching this might want to do it in Drive. I feel like this is a good stopping point. This week I'm almost at the 45 minutes is a good length. Yeah, so there's just a lot more to do, and then I think I might want to actually do this in Drive. So that's going to be it for this video. In the next video, I think I'll set up this notebook in Drive just to show that it can be done, and go through the notebook. So that's it for this video. Thanks for watching. See you in the next one.